So in this video, we're basically going to be reviewing whether or not you're going to be using theoretical or experimental probability when making a prediction. At this point, you know the difference between the two. You know that theoretically is kind of like a hypothesis. That's what we expect to happen. And then experimentally, when we have results, we can compare what actually did happen to what we would have thought or predicted. So to get us started here, we have a spinner. It's divided up into 4 equal sections. And so the probability of landing on A would be a 1 out of 4, which is 25%. The probability of landing on B, 25%, C, 25%, and D is also 1 out of 4, 25%. So if we're going to be spinning this spinner 4 times, theoretically, we're predicting that we're going to land on each section once. All right? They each have a 1 out of 4% chance. So now for question 5, what it's saying is, if we spin the spinner 12 times, how many times do we expect to land on A? Now, once again, we haven't started any trials. We haven't conducted any trials. We have no results. So we're still going with theoretical probability. And therefore, we're going to be using our theoretical probability to make our prediction. We want to know the theoretical probability of landing on A, and we already figured that out is 1/4. So we're going to be using that to predict how many times out of 12 trials we'll land on A. So we're going to use 1 out of 4 to predict how many out of 12. Well, if we're conducting 12 trials, we're conducting 3 times the number of trials. So our scale factor is 3, and 1 times 3 is now 3. So we would expect to land on A 3 out of the 12 times. Now with a calculator, I'm going to divide 3 by 12. And that's, again, 25% of the time we would expect to land on A. All right. Now we have that someone is going to spin the spinner 32 times, and we want to know how many times do we expect to land on each letter. So this is the proportion that we're setting up. And once again, we're using the theoretical probability. We don't have any results yet. So we're using theoretical probability to make our prediction. When we cross multiply 1 times 32, we get 32. And when we divide by 4, we get 8. So X here would be 8. So 8 out of the 32 times we'd expect to land on A, 8 out of 32 B, 8 out of 32 C, and 8 out of 32 times would be D. Once again, in the calculator, we want to make sure that the 8 out of the 32 is the same percent chance, and it is 25%. All right, cool. So let's fill out this bottom section now together. To predict the number of times that we're landing on each section, we just simply set up a proportion. Now, to set up a proportion, we've done this a lot so far this school year. We're going to start with what we know. And the thing that's given to us right now is the theoretical probability. And we're using that to then set it equal to an unknown out of the total number of trials. So we started with theoretical, put X over 32. In this scenario, since we are conducting 8 times as much, we multiplied the numerator by 8, and that is called the scale factor. So 4 times 8, 1 times 8, we have a scale factor of 8. Once we have multiplied by that scale factor, we have correctly predicted the number of times we expect the event to occur. So this is all theoretical. All right, now let's flip over. So now what we have up top is that we actually conducted an experiment and spun the spinner 32 times. So now we've conducted an experiment. These results are going to be our experimental probabilities, okay? Looks like 8 of the times she landed on A, 9 of the times she landed on B, 10 of the times she landed on C, and 5 of the times she landed on D. I want to remind you guys that over here, this is everything for what we would have expected theoretically. We know that each of these has a 1 out of 4 chance, or 25%. So we would have expected 8 out of 32 for A, 8 out of 32 for B, 8 out of 32 for C, and 8 out of 32 for D. We had 8, 8, 8, 8 in our theoretical prediction. Now this table right here is actually the results. So we now can compare that 8 out of the 32 for A was exactly what we expected. Now for B, she landed on B 9 of the 32 times. So that was more than expected. And we can see that 9 is more than 8, but let's get a percent real quick. If we do 9 divided by 32, we can see there that's about 28% of the time, 28% of the time. So that's a little bit more than we would have expected compared to the 25%. Now let's see for C, the 10 out of the 32, what percent that is. So that's going to be about 31% of the time. So once again, more than what we would have expected. Now for the last one, she landed on section D 5 of the times. And we know that 5 out of 32 is less than 8 out of 32. And let's divide now with a calculator. So that 0.6, I'm going to round that up to about 16% of the time. So the 16% is less than what we would have expected at 25%. So the first one was exactly the 25%. And we had 2 more that were more and 1 less that was less than what we would have predicted. So you can see now we're comparing what happened to what we expected. So when making our predictions, we can make our predictions based off what we think, which is theoretical, or we can make our predictions based off the results of an experiment or survey, which is us using the experimental probability. Okay, make sure we got experimental there. So let's take a look at a couple of experimental probability predictions. Okay, this is when you're going to want to use the data that you have to make your prediction. Now, so far, this scenario, I want to point out that we made predictions based on theoretical probability. We predicted that she would have landed on each one of these sections 8 of the times. Then she conducted an experiment, and we can see that she's actually landing on C more times than expected and D less times than expected. So if she was going to spin the spinner again, based on the data, we can now argue she's more likely to land on C than any other section. But going into it, before we had the data, we would have said that they all were equally as likely. So now for this first question down here, Michael has made 10 out of 15 free throws. So this information that we're given, this ratio that we've been given, this is experimental. And we're going to use that data to predict how many he's going to make if he's going to shoot 60 total. Now, some of you can catch that 15 times 4 gives me 60. So then you see a scale factor to do 10 times 4 is 40. Not everybody sees that. So if you want to cross multiply over here, you can do 10 times 60 and get 600, and then divide it by the 15, and you'll still get the 40. So the idea here is that we have some data to use to predict how many free throws that Michael will make. Now, he's currently a 67% free throw shooter. If we take 10 and divide it by 15, he is a current 67% free throw shooter. That's better than the theoretical 50-50 that we know everybody is. Now, theoretically, I want to remind you guys, theoretically, we would have expected him to make half, 30 out of 60. But since he's doing better than half, we've predicted that he'll make 40 out of the 60. And at that same rate, he's still that 67% free throw shooter that he's already currently proven that he is. All right, now for the next one. In a recent survey of third period, 18 out of 25 students said that they had their own device in school. So we've been given the results of some data. So once again, we're using experimental probability. Now going into the survey, you either do or don't have your own device. So we know that we'd expect like half students, like theoretically, half the students are going to have a device and half won't. But we actually conducted a survey, and now we have some results to see that 18 out of 25 are actually bringing in their own device. So we can use that to predict how many out of 150 students will have their own device. Now, if you ask yourself how many quarters go into $1.50, I think a lot of you would catch that 6 quarters would go into $1.50. So some of you can catch a scale factor of times 6. So if you do 18 times 6, we're going to get 108 students. It's okay if you don't catch the scale factor. You can cross multiply this 18 times 150 and get 2,700 in the calculator. And then you can hit divide by the 25 and you'll still get 108 students. Okay? Once again, we want to see if our percent is consistent. Currently, if there's 18 out of 25 who have their own device, we have 72% of the students who are bringing in their own device. So now let's check for the 108 out of 150. It's still 72%. So we're using, in this case, we're using the experimental results to make our predictions. All right, now let's go to the next page. So now we have a new scenario where Samantha took a survey of students' favorite class subjects. And in the survey, it looks like she's got the following subjects. Okay, she's got math in the survey, gym, English, history, art, and tech ed. So she's got 1, 2, 3, 4, 5, 6 different classes in her survey. So going into the survey, each class has a 1 in 6 chance of being voted as somebody's favorite class. When we divide that in the calculator, that's about a 16.7% chance. So I'm going to move that a little bit further and round to just about 17%. So each class has a 17% chance, theoretically, of being voted as a student's favorite class. Now, according to the results, though, we can see that only 26 voted for math, 70 voted for gym, and so on. We've got all the results in there. So the first question we're asked here is, what is the experimental probability that a student will like history the most? Now, the experimental probability is going to be based right here off of the data, and we have 32 out of the 200 students who said that they like history. 32 and 200 are both divisible by 8, and so if you want, you can just reduce by 2, divide by 2, divide by 2. But the goal is to realize it reduces all the way to 4/25, which is about 16%. Now, if I compare that to the theoretical probability, we can see that the results pretty much matched up with what we would have expected to happen, okay? All right, now let's take a look at part B. Now, if we were going to conduct a survey out of 600 students, how many would we predict to say history is their favorite? So we have results. So we're going to use the results of our survey to make the prediction. We're not going to use the 1 out of 6 to predict and say 100 out of 600. No, 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 no. Because when you actually have data to work with, the data paints a better, more realistic picture. So using the data, we can see that we're going to predict if we have 3 times as many students in the trial, in the survey, we're going to expect 3 times as many people to say that they like history. Now, if you don't like the scale factor method, you can cross multiply. 32 times 600 in the calculator is 19,200. And then when I divide it by the 200, we're going to get 96 students. Now, I do want to point out, I'll put in blue here, that theoretically we would have predicted that each subject has an equally likely chance. And if we were going with theoretical probability, our answer would be 100 students. So theoretically, we'd predict 100 students, and according to the survey, we get just a more realistic expectation that we won't quite get 100, okay? All right, now for the next one. Out of only 100 students, we're going to take a look now at art. So art, we had 18 up top, 18 of my 200 in the results. So now how many of 100? So if we have half as many students in the survey, we're going to expect half as many people to say that they like art, so 9 students. Now for the last question, we're exploring how many then say that they like tech more than gym. So how many up here picked tech? Now if they picked tech as their favorite subject, we know that they obviously like it more than gym. So we have 10 out of the 200 who said that tech ed was their favorite class. And folks, if we only now are going to survey 20 students, we're dividing by 10, okay? We're taking a 10th of the students and surveying them, so we expect a 10th of the students to say that they're going to pick TED over gym. All right, so just 1 out of the 20 students will likely vote for tech, okay? Now what you're going to do is I'm actually going to have you stop and attempt the rest of the page on your own. I do want you to stop the video or pause the video, and then I want you to try it, and when you're done, you can hit play and scroll down and see how you did. All right, so go ahead and hit pause, and when you hit play, it'll be ready. All right, so now that you've hit play, we got that for 4A. Jocelyn has missed the target 12.5% of the time, and we can use that result to predict how many times out of 160 she'll miss the target. Folks, if she is missing the target only 12% of the time, that means Jocelyn is really, really, really good at what she is doing here. All right? Double check your answers down here that you've summed up correctly. And now this bottom part, there is no answer. There is no answer for if theoretical or experimental is a better prediction. But in general, if you have data, the data is going to give you a better idea of what to predict. So when you have data, you're more likely going to want to use the data to make predictions, but in some cases we can't. For example, if your mom and dad are going to have, like for you, a baby brother or sister, you can't use your gender as data to try to predict their gender. So when talking about the gender of a child, we have to go with theoretical probability in terms of 50-50. So it really depends on the scenario which one we're going to go with here, folks. And now that you're done with the video here, you can go ahead and hit stop. We're done. Thank you.